Hey everybody, my name is Chris and I'm a tutor here at Chegg.com. I mostly do math and a little bit of computer science, and in this video we're going to do an example of the wave equation. So specifically we're going to solve the wave equation. So we have the second partial of u with respect to t equals the second partial of u with respect to x, where x is any real number and t is positive. And we also have the initial conditions, u of x comma 0 is 0. And u sub t of x comma 0 is xe to the minus x squared. Okay, so to solve this, we're going to use D'Alembert's solution, which says, so let's come off to the side here, separately down here. And in general, so we're going to first state D'Alembert's solution in general, and to do that we have to give the general wave equation in this context here. So in general, we have u sub t equals c squared u sub xx, where minus infinity less than x less than positive infinity and t is positive. So in other words, x is any real number and t is positive, so there are no boundaries on x. And in general, we also have u of x comma 0 equals f of x, and u sub t of x comma 0 equals g of x. Okay, so D'Alembert's solution says that under these conditions, u of x comma t equals 1/2 times f of x plus ct plus f of x minus ct plus 1 over 2c times the integral from x minus ct to x plus ct of g of s ds. Okay, so how do we apply this formula to our specific case? Well, in our specific case, what do we have? We have, here's our f of x. Okay, it's 0. Here's our g of x. It's xe to the negative x squared. And what's our c? Well, our c is just 1 because this is 1 times u sub xx. So that's our c. Well, technically that's our c squared, but then we want c to be positive, so c is going to be 1. So that simplifies things a little bit. So in our case, our u of x comma t is going to be, well, here's our f of x. So if f of x is 0, always 0, then it's still going to be 0 even if we have x plus ct or x minus ct. So in our specific case, this entire thing is just 0. So it's all just gone, 0. Okay, so all we really have left is 1 over 2c. Remember, c is 1. And then we have x minus ct, the integral from x minus ct to x plus ct, but again, c is 1, of g of s ds. Well, what's g of s? Well, g of x for us is xe to the negative x squared, because remember this is g, and what that means then is that g of s, I'll just write it in the integral, g of s therefore is se to the minus s squared ds. Okay, so let's go ahead and go to the next page and evaluate this. So this is going to give us a formula for our u of x comma t. So basically what this comes down to is simply evaluating this integral. So let's go ahead and do that. So we have u of x comma t equals 1/2 times the integral from x minus t to x plus t of se to the minus s squared ds. Now we're going to have to do a little substitution here. So usually we use u for substitutions, but the variable u is already taken. So let's go ahead and use v. So we're going to say let v equal negative s squared. So then dv is going to be negative 2s ds. Okay, so let me first rewrite this integral. It's going to be 1/2 times the integral from x minus t to x plus t. And then what I want to say is e to the negative s squared. And then what I want to do is say times, leave a little bit of space, s ds. Now I want negative 2s ds, so let me put a negative 2 in here. But if I'm going to multiply by a negative 2, let me actually use a different color. If I'm going to multiply by a negative 2, then I have to divide by a negative 2 out here, or in the integral, to make that okay. Okay, so now, well, how does that help us? Well, now we see that this negative 2s ds, that is dv, and this right here is e to the v, because remember, v is negative s squared. So then what we end up with is, so 1/2 times 1 over negative 2 is just negative 1/4. And then we have the integral, and we have to be careful and change our limits. I'll come back to that. So this is e to the v dv. Now, what about the limits? Well, if v is minus s squared, then s ranges from x minus t to x plus t. So when s equals x minus t, what's v? V equals minus x minus t squared. And similarly, when s equals x plus t, v equals minus the quantity x plus t squared. Okay, it's just that simple, because remember, v is minus s squared, so when s is this, v is just minus that squared. And when s is this, v is just minus that squared. Okay, so this is going to be, oops, go back to green. This is minus x minus t squared, and then this is minus x plus t squared. So it's just a matter of evaluating this integral here. So let's actually go to the next page. So on page 3, we're going to have negative 1/4 integral from negative x minus t squared, that's a squared, to negative x plus t squared. And remember, we had e to the v dv. So if we want to integrate e to the v dv, we're just going to get plain old e to the v. So we have negative 1/4 times e to the v, where v goes from negative x minus t squared to negative x plus t squared. Okay, so this is negative 1/4 times e to the negative x plus t squared minus e to the negative x minus t squared. And that's actually pretty much it. That is our u of x comma t. And we could simplify that if we distribute the negative 1/4 or possibly even just the negative, simplify things a little bit, but it doesn't really matter. So here, our u of x comma t is equal to negative 1/4 times the quantity e to the negative x plus t quantity squared minus e to the negative x minus t quantity squared. So this has been an example of using D'Alembert's solution to solve a partial differential equation, specifically the wave equation. I hope you found this video helpful, and thank you for watching.